Hey guys, Mr. B here, and in this video we're going to be going through chapter 12.1 on forces. So there is a lot of vocabulary in this section. We're going to be learning about force and different types of friction and all kinds of stuff. So, we just got to keep some words straight, but either way, let's jump into it here, okay? So first off, what is a force? Now, if you're like me and you think of the word force, I think of Luke Skywalker and Darth Vader and use the force, Luke. No, not that kind of force? Okay. Well, in physics, we have forces. And a super simple definition for a force is just simply a push or a pull acting on an object. Okay, that's it. So forces, of course, are all around us. Forces cause objects that are at rest or not moving to begin moving, or objects that are already moving. Forces can cause them to accelerate by either speeding up, slowing down, or changing their direction. Okay. Now, forces are pretty easy to measure. A lot of times we can use what we call a spring scale, which is basically something that has a spring in it, and as the spring is pulled, it will register how much force is being applied by pulling on that spring. You may have seen these in grocery stores before. If you put your fruit or vegetables on a big basket and it weighs down and there's a big circle with a little arrow that spins and tells you how many pounds it is, that's a spring scale. If you've ever gone fishing and you've hooked a fish up onto, the things you hook the fish on and it hangs, that's a spring scale. Your bathroom scale is probably a spring scale. There's springs underneath it, and as you step on it, the springs get pushed down, records how much force is being pushed on it. So the unit that we measure forces in is called the Newton, okay, abbreviated with a capital N. This may or may not be a unit you've heard of before, but we'll have to get used to using this term because we're going to see it all the time. Now, forces are vectors. Okay, now we've learned about vectors in previous chapters with displacement and velocity and acceleration, and now we're bringing vectors back again. So forces are a vector. They can be represented by an arrow. The longer the arrow is, the larger the force. The smaller the arrow, the shorter the force. And because it's a vector, there's also a direction component. So it matters which direction the force is being applied in, okay? So all the vector math that we've done so far up to this point, we are going to continue to do, okay? A vector addition, all that stuff. All right, now there are some practice problems here. We're going to skip past these. These, of course, will be in the quizzes practice at the end of this video, so just keep on moving. All right, so now, since we are dealing, of course, with vectors, when we have multiple forces acting on an object, we can combine them pretty easily. Okay, remember, forces acting in the same direction can be added together. Forces acting in opposite directions can be subtracted from each other. And if they're at right angles to each other, like a triangle, then we'll have to use the Pythagorean theorem, but we can, of course, calculate the forces there. Now, like in previous chapters, when we have multiple vectors and we have to add them all together, we get what we call a resultant vector, right? Or like with displacement, it was our resultant displacement, or velocity, it was a resultant velocity. Same thing with forces here. Once we've added together all our forces, subtracted them, whatever we're left with, we call this our net force. So the net force is the overall force acting on an object after all the forces have been combined. Usually it's going to be pointing in some direction and have some amount of size to it, okay? Now there's two types of forces that we're going to be dealing with. We're going to be dealing with balanced forces and unbalanced forces. So balanced forces, as it sounds, are when you have multiple forces that balance each other out or cancel each other out. So balanced forces could be like, for example, in a game of tug of war. You've got two teams. They're both going to be tugging on this rope, but each one is pulling with 200 newtons of force in the opposite direction. And since we have two vectors, both pointing in opposite directions, if you subtract them, they would give you a net force or resultant vector of 0, meaning that they are balanced, okay? So when you have balanced forces, there's no change in motion. So if the object is sitting still, it will remain sitting still. If it was moving already, then it will continue to keep moving, and it will not speed up or slow down or change direction, okay? But most forces are unbalanced, which means that you have two forces or more, and one of those forces is going to be larger than the other forces. So since we have a force that is larger than the other forces, oftentimes we're going to have a net force that is not equal to 0. So basically what this means is one of those forces will be larger than everyone else, and if you subtract them or add them all together, you're going to have a result that is not equal to 0, which means you're going to have some amount of force left over pointing in some direction, and then we will have a change in motion or some kind of acceleration, okay? So with unbalanced forces, your object is going to accelerate. Again, that means speeding up, slowing down, changing direction. All right. So here's just a real quick example of showing you some force vectors. We can add forces together that are in the same direction. So two forces that are both 5 newtons would add together to give a net force of 10 newtons going in the same direction. If you have two forces that are in opposite directions, you would subtract them from each other because they're vectors. So if we have 5 newtons going to the right and 10 newtons going to the left, we'll have negative 5 newtons, or 5 newtons going left. Negative, we can just disregard. Or of course, if they are equal in size and opposite direction, they will cancel each other out to give you 0, which in case that would be balanced forces instead of unbalanced. All right, so when we talk about forces, one of the main forces that we really want to know about is friction. Okay, friction is a force that is all around us all the time. You cannot escape it unless you were to go into outer space, and even then, there is still a little amount of friction, but it's relatively frictionless. So, what is friction? How we define friction? Okay, now in physics, friction is defined as a force that is always trying to oppose the motion of an object. So what this means is anytime you have a moving object, friction is always trying to push against that object, okay? So typically friction always slows things down, if you want to think about it that way, right? It's always trying to slow things down. Now there's 4 main types of friction. There's static friction, sliding friction, rolling friction, and fluid friction. Okay, so we're going to each one of these and what they look like and how they work so we can understand. Okay, now static friction is the first type. Now the word static, you might think of the word static and think of like static electricity, right? Like shocking or lightning bolts or something. But the word static means non-moving. So if something is static, that means it's not going anywhere, it's not changing. So static friction is the friction that keeps non-moving objects staying in place, okay? So anything that's sitting on your table or anything that's motionless stays motionless because static friction keeps it there. If there was no static friction, then you would set something down on a table and it would just like slide around and it would never stop moving, which would be really weird and hard to grab things, right? So this picture shows a box, and if you were to push on that object, let's say it's a really heavy box, right? If you were to push on it, it wouldn't go anywhere at first because static friction keeps it rooted to the ground. However, once you apply enough force and you overcome the static friction, which keeps it rooted to the ground, it will begin to move, and at that point it will become sliding friction. So sliding friction, as it sounds, is friction that opposes the motion of two things sliding past one another. Okay? Now sliding friction is weaker than static friction. So once you get an object moving, it's easier to keep it moving than it is to have it stop moving and then have to get it moving again. So this is why, like, again, if you ever moved anything heavy, once you start going and get it moving, you're typically just like, okay, keep going, keep going, keep going, because you know that as soon as it comes to a stop, it's going to be difficult to get it going again, right? Because once it's moving, it's easier. So sliding friction is relatively weak. From here, then we have rolling friction. Now, rolling friction, as it sounds, is the friction of rolling objects, right? Now, rolling friction is much, much, much weaker than static and sliding friction. It can be about 100 to 1,000 times less the force of static and sliding friction. And this is primarily the reason why we put really heavy objects on wheels, right? Our cars have wheels. Whenever you're trying to move a bunch of really heavy boxes, you might put them on a dolly, which is something that has 2 wheels, and you kick it, you tilt it and you push it forward. Wheelbarrows have wheels. Skateboards, right, have wheels. Wheels have rolling friction, which is much, much weaker. It's much easier to roll something than it is to push or slide something, okay? The last type of friction we have here is fluid friction. Now, the word fluid, you might think of water or a liquid of some kind, but a fluid is pretty much any material that has liquid-like properties or is able to flow. So liquids certainly are fluids, but gases are also fluids, okay? Air is a fluid. If you've ever seen like a fog machine, right, or dry ice when they put it in water and all the fog stuff comes up, you can actually put it in a cup and you can pour it, okay? Gases are fluids just like water or liquids are fluids. So anytime you try to push your way through a fluid, whether it be a liquid or a gas, there's always going to be some amount of friction pushing against you. And the interesting thing with fluid friction is the harder you try to move through the fluid, or the faster you try to move through the fluid, the more it pushes against you. This is the reason why if you've ever been in a swimming pool before and you tried sprinting or running before, right? If you've ever been with a friend and you're like, hey, first one to the edge to get out, right? I'll race you. And you're like, and you try running, you don't go anywhere. Because the faster you try to move, the more the fluid pushes against you, and therefore the slower you go. So, it's easier to just simply walk through a fluid than it is to run. And this can also be like felt in other ways. So if you've ever, taken your hand, if you take your hand, you do this in front of your face, you're going to feel the air on your hand. It's not super strong, but you can feel it, right? However, if you're in a car and you stick your hand out the window, your hand's going to go, it's going to get blown backwards because you're moving at 60 miles an hour through the air then, whereas doing this, it's maybe only moving 2 miles an hour. The faster you try to move through a fluid, the harder it's going to push against you, okay? So fluid friction has relatively low strength, but it ramps up really fast, which is a key thing to know. And the picture here is not correct either, so. All right. And then one of the other forces that we deal with on a regular basis is gravity, right? So gravity is a force that is constantly trying to pull you down to the floor. Gravity is a force that acts between two masses, typically large masses, because if you're not large enough, you don't have your own gravity, right? Like us, like we're not large enough, we don't have our own gravitational field, but planet Earth does. So gravity is an attractive force. It pulls two objects together. This is a force that we cannot escape, that is on us all the time. Even up in outer space, technically you are still affected by Earth's gravity. It's just much, much, much weaker. So gravity is always acting downwards. Okay, this is an important thing to know. It's always acting downwards, never at an angle. Okay, not diagonally downwards or whatever. It's straight downwards, always. So when we start talking about force diagrams and drawing forces later, this is something you're going to want to remember. Okay, so keep that little nugget of information in your mind. So objects that are falling, of course, are falling because of gravity. Gravity causes these objects to accelerate downwards. Whereas as they fall, air resistance or fluid friction is always going to be pushing upwards on those objects in the opposite direction, which of course is going to reduce your acceleration. This is a really important factor because this is why parachutes work, right? If you jump out of an airplane, you're going to fall through the air, and you're going to feel it as you're falling. You're like, oh, and your clothes and your lips and everything's flying. But you're eventually going to reach what we call terminal velocity, which is basically where this force of the air pushing against you as you're falling and gravity pulling downwards, those two forces are going to equal out on each other. So gravity is going to be pulling you down with some amount of force. Air resistance is going to be pushing you up with the same amount of force, and they will balance each other out, at which point your net force is now 0, and you will no longer accelerate. Okay, so you'll reach your maximum speed, again, what we call your terminal velocity. So this is where you are falling at a constant speed. You're not speeding up, you're not slowing down, and it's because these two forces, gravity pulling downwards and fluid friction pushing upwards, balance each other out. And then, of course, if you pull a parachute, you're now going to increase the amount of fluid friction there is, which will reduce your speed even further to a point where you can safely, touch the ground and you're not going to go right and turn into a pancake. So, but all of these things, again, work based on forces. All right. The last thing to talk about here is projectile motion. We will deal with projectiles a little bit later in this course, but whenever you have an object that's flying through the air, there's typically going to be one force acting on it, which is gravity, okay? So typically something might get given an initial force sideways, but then once that push is given, the only force acting on it at this point is gravity. So gravity causes it to fall downwards, and so it can't just go straight down. Instead, you get a curve. So as the object starts to go sideways, gravity pulls it downwards, and you get a resultant that basically makes it curve diagonally. This is what we call a parabola, okay, also known as projectile motion. And this is going to be a very common thing that we see all the time, right? So here's a picture here showing two balls falling. One is a red ball, one is a yellow ball. And the red ball is falling straight down. The yellow ball was given an initial push sideways. You see that the yellow ball has a curve to it as it falls, and the red ball falls straight down. Now, interesting thing to note here is, even though the yellow ball was given a sideways push, they both fall at the exact same rate. Okay? Even though the yellow ball was thrown or pushed sideways, they both fall at the same rate, and that's because the same force is causing both of them to fall, and that's gravity. And gravity always acts downwards. So if you have an object that was given a push sideways and then it falls versus an object that just falls right away, it doesn't matter. They're both falling due to the same force, which means they both fall at the same rate. So if you look at this picture, you'll see the red ball and the yellow ball are right next to each other in every single frame, right? Every single frame, the red ball and the yellow ball are at the same exact height as they fall. It doesn't matter that the yellow ball was given a push sideways first. They both fall at the same rate because they're both falling due to the same force, okay? So a little interesting piece of information. That one's a little bit tricky to kind of come to concept with, but it's something interesting to know. So, all right, guys, that's it for this section of notes. Hopefully that helped you, but as always, if you have any questions, feel free to reach out to me. Send me an email. We can talk in person, anything along those lines. So, all right, guys, that's it for this one. I will see you in the next one. Bye.